Hello and welcome back. I'm Matthew Lay, and today we are going to study Watt's law, which is a study of electric power. We have some objectives in this lesson. We want to list that fourth basic measurement of electrical circuits. You could probably guess what it is. And calculate power in a circuit given voltage and current. Okay, so that fourth measurement, three basic measurements we've talked about so far is we need electromotive force that is needed to cause the electric current or amps to flow through some sort of restriction measured in ohms. The fourth measurement exists in every circuit that has electric current flowing through it, and that's what we're going to talk about here. So when we study this, we're actually studying this gentleman's work, James Watt. He was a Scottish inventor and a mechanical engineer. He was a little bit of a chemist as well in the late 1700s and early 1800s. He was best known for improving the steam engine and bringing it into the Industrial Revolution. He actually had a Watt steam engine named after his name. But he developed the concept of horsepower, measuring the power output of something. Now, we still, with electric motors, rate them in horsepower, which technically is an imperial unit, which is the imperial system is what we also call the standard system. It's the mile, the inch, the foot, the pound. But the System International unit was named after him, the watt, because of his groundbreaking work. So watt is a unit of energy transfer. Okay, so when we have current flowing through some sort of resistance, we have energy transfer. And that energy transfer happens in all components in a circuit. Energy transfer is termed power. The letter P is used in formulas to represent power, which is measured in watts, represented by the letter W. Okay, so P for power. Technically, it's active power. When we get into alternating current, we're going to learn that there are multiple types of power. But now when we're dealing with DC and resistors, all power is going to be active power. So P is for active power in the formulas. And active power will always be measured in watts. Most commonly known for energy transfer of an incandescent light bulb, we still, even though we use non-incandescent bulbs like LEDs and compact fluorescents, we still rate them as the equivalent of what an incandescent bulb would give off, like a 40-watt bulb or a 75-watt bulb or 120-watt bulb. 1 watt of energy is transferred when 1 volt of electrical pressure forces 1 ampere of electrical current through 1 ohm of resistance. Okay, so you notice it's a bunch of ones here. So they're all tied together. The singular unit of each one of these measurements is associated with a singular unit of all of the others as well. So simply put, 1 watt equals 1 volt times 1 amp. So now we are given this shape here. We already learned about the Ohm's law triangle. This is the Watt's law triangle, and it works the same. So we have power, P for power, I for current. Remember I, the intense feeling you feel with current. E for electromotive force, or our volts. And if you cross over the horizontal line, you're doing a division. And if you cross over the vertical line, you're doing multiplication. So if I cover up any one of these letters, I can find my math formula. So if I cover up the P, then I'm only left with the I and the E. So P equals I times E. If I cover up the E, then I'm going to find the formula for, if I know the power and I know the current, I can find the voltage. And that would be P divided by I. And then if I cover up the I, you notice that the P has to cross the horizontal line to get to the E. So I equals P divided by E. Those are our three formulas that we can get from this triangle. So now down here, this is a new concept. This is a schematic, and a schematic is a representation on paper of physical components in real life in symbolic form. So this right here, this circle with the plus and the minus, is going to replace our battery moving forward. I'm not going to have presentations that show a battery and then show light bulbs or something, pictures of resistors. We're going to actually start using the schematic symbols. So right here, the circle kind of even looks like a battery looking down from the top. Of course, on a D cell or a C cell, we don't have the positive and the negative on the top of the battery. The positive is on the top and the negative is on the bottom. But here in this symbol, this circle is meant to be a power supply, and this is a direct current power supply because we have a plus and a minus. If it's alternating current, we have a different symbol inside the circle. We'll get to that. But this is meant to be some sort of direct current power source. And then what this symbol is representing is a resistor. So if you, the shortest distance between 2 points is a straight line. Well, if you have a zigzag line like that, that means you're adding some resistance or adding some length to what has to travel down that path. So if electrons have to travel down this path, it's meant to show that there's going to be some restriction, and that is our symbol for a resistor. Now we know that E represents voltage in our math formulas, so that's why it says E there. And the R here means that it is a resistor, and that's going to represent our resistance. And these are generic terms. Of course, on worksheets, I will give you quantities for those. You notice there's a subscript T here. That means that's the total voltage. Okay, that's all that T means. It's the total voltage. It's the voltage that's coming out of the battery. If there were multiple components in here, each one would consume a certain amount of voltage, and we would have a different subscript for those. And then here for the R, the 1 just means this is the first resistor. If there were 2 resistors, there would be an R1 and an R subscript 2. Okay, so this is the simplest circuit that we can create. One DC power source and one battery. So if our battery or our DC source is 1 volt and our resistor is 1 ohm, this is just proving out that example that I gave you on the previous slide, we're going to go ahead and use Ohm's law, and I equals E over R. So if we take 1 volt divided by 1 ohm, volts divided by ohms, we'll change the units to amps. We get 1 amp. Okay, so now we can use our Watt's law triangle here. And we know if we're trying to figure out power and we know our current and our voltage, we can calculate our watts. So here, if I'm trying to solve for P, I cover up that letter, and it is I times E. So that's why that formula says I times E. And of course, we know that we have 1 current and 1 volt. So you multiply those together, and you get 1 watt. Okay, this was a short lesson. We're going to do a quick review here. Name that 4th measurement of the electrical measurement. Okay, so if you want to pause and come back. It is power, and power is measured in watts. Whenever we have voltage and current in a circuit, we have power. And at the beginning of this, you notice I showed a watt meter from outside a residential home. That's what you actually pay your bill on. It's because voltage can fluctuate up and down, and so can the current. But when you multiply those two together, you know how much energy you have used, how much work has been consumed by the home, and therefore that's how much you pay the electric company. And you want to calculate the power of a circuit that has an 8-volt battery source, and the current in that circuit is 250 milliamps. So if you want to take a moment and calculate that and come back. Okay, P equals I times E. And here I transposed it, E times I. Remember, the commutative property for multiplication exists, so E and I, the order doesn't make a difference. To solve this, all we have to do is take 8 volts times our 250 milliamps here. And when we multiply those together, that's basically taking 8 times 0.25, because we have to take into consider milli. So 0.25, 8 times 0.25 is going to equal our 2 watts. That concludes our lesson on watts and electrical power. I hope that was helpful, and we'll see you in the next lesson.